Okay, so let us look at post-hoc test today. To conduct a post-hoc test, you need to conduct your ANOVA first. Your ANOVA need to have this conclusion that your null hypothesis, if your null hypothesis fail to be rejected, then you do not need to do post-hoc test. If your null hypothesis is rejected and that you accept your your alternative hypothesis, then you can continue with post-hoc tests to determine which group of treatments are actually significantly different. So a post-hoc test is actually a follow-up test to the ANOVA when there are two or more groups. So it's a test whenever a significant difference between two or more sample means has been revealed by ANOVA. You follow up with post-hoc tests to determine which group of the treatment are actually significantly different. In this class, we are going to look at two different types of approach to conduct our post-hoc test, which is the LSD, least significant difference test, and the DMRT, Duncan's multiple range test. You can use any of these tests to conduct your post-hoc test in this class. But of course, there are some consideration for you to think about before you choose which type of post-hoc test to be conducted. So let's look at the first one, least significant difference, LST. LSD test is carried out to actually determine which pair are significantly different. So if the treatments were conducted with the same number of replication, means that each group of treatment, they have similar replication number, then you use this formula to do your calculation. So R over here is the number of replicate, so it will be the same. MSE over here is the mean square of error where you can plug from your ANOVA table. And T alpha here is the number that you need to refer to your T table. And LSD alpha, so alpha is the significant level that we need to calculate. So for your T value that you are going to get from your T table, so you need to do it, you need to refer to the two tails. So it's a two-tail test because we claim that there is difference or there is no difference between the two groups. So therefore it's a two tails because there's no direction. So for any of your alpha, so it need to be divided by 2. So we will look at the example later on. However, if each of the treatment group, they have different replication, then you need to follow this formula where instead of like divided by R, so it will be divided by R1 and the sum of R1 and R2. So that's because they have different replicate number. So how do you interpret the result of LSD? So if the difference between the means is larger than the LSD calculated, then the difference is significant. So at the significance number of level of alpha. If the difference between mean is smaller than LSD, then the difference is not significant, not significantly different. Let's look at the first example. So for this example, you have actually conducted the calculation in your ANOVA lecture. So let's refresh a little bit and look at it again. So one trial was conducted to determine the effectiveness of 6 types of pesticide, RS1 to RS6, and also the control. So in how many replicates? 4 replications, 1, 2, 3, and 4. With an experimental design CRD. Does the pesticide increase the grain yield by preventing the pest diseases? So the hypothesis is H null, the null hypothesis is the means of all treatment groups are actually similar. And the alternative hypothesis claim that there are differences among the mean of the treatment groups. So if you were to refer back to the calculation that we have done in our ANOVA test, so we have obtained this ANOVA standard table where we have like calculated the 5% and 1% significant level with F calculated, the F value calculated at 9.83 and the critical value referred to the table is 2.57 for 5% significant level and 3.81 for 1% significant level. So from this result, so you are able to conclude that there are actually differences among each treatment group over here. But which one is different compared to another one, we actually do not know. So the conclusion based on this ANOVA table is the null hypothesis is rejected and therefore there are differences among the treatments. The question over here is which treatment group is different from the control? So the question over here asks which does the pesticide increase the grain yield? So if we want to know whether if this treatment actually increase the grain yield, we will need to compare with the control. So for this question, so we are comparing RS1 to control, RS2 to control, RS3 to control, RS4 to control, 5, 6 to control. So that is what we are going to compare later on. Since ANOVA conclude that there are differences, so we need to follow up with the post-hoc test to determine which group are actually show significant differences. Okay, so we are using LSD. So there are 4 steps over here. Step 1, determine the T value. Step 2, calculate the LSD. Step 3, calculate the differences. Step 4, make the conclusion. So let's look at the first step. So this is the ANOVA table that you have calculated in your ANOVA, and you have get your degree of freedom 21 for degree of freedom error at 21, and mean square for your error is 94774. So these are the 2 numbers that you need to plug in to your LSD. So this is the formula of LSD. We are using this formula because all of these replicates, it has the same replication number 1, 2, 3, and 4. So therefore we use the first formula. So T alpha is the T tabulated for 2 tail at significance level of alpha and degree freedom of error. So this degree of freedom error is 21 over here. So mean of square is this one. So let's calculate for the 5% T value. So the T value is this one T alpha. So the degree of freedom for error is 21. And at 5%, so remember we are working for 2 tails. So therefore it will be 0.05 divided by 2. So you get 0.025. Go to your T reference table, look for degree of freedom 21, which is this one, and look for 0.025. So go down, so this is the number that you get, 2.080. So what about 1%? So the degree of freedom for error, it will be the same, 21. Then because it's a 2 tail, so 1% it will be 0.01 divided by 2. So you get 0.005. So 21, 0.005. So you get 2.831. So these are the T values that you need to remember. Let's move on to second step. So in second step, you need to calculate the LSD value. So how to calculate the LSD value? So you need to follow this formula over here. So since you have obtained your t value, so what you need to bring in is actually just the mean of square over here. So for 5% significant level, you just need to bring this in 2.080. So times the square of 2 times 94774 divided by 4, replicate, and you get 453 for your 5% significant, and for your 1% significant you get 616. So let's move on to step 3. Calculate the differences. So remember, your LSD for 5% significance is 453, whereas your significant level, the LSD for significant level 1% is 616. So you calculate the means. So these are the information that has already been provided. So what you need to do is calculate the mean for each treatment group. So RS1 has a mean of 2,127. How do you obtain this one? That's a sum of 2537, 2069 plus 2104 plus 1797 divided by 4. So you get your mean. Calculate the mean for each treatment groups over here. And then calculate the difference with control. So how do you compare with how do you calculate the difference with control is 2127 minus of the mean of control 1316, and you get 811. For RS2, 2678 minus of 1316, and you get 1362. So you calculate for all the group over here. There's no number for control because 1316 minus of control again 1316, you get 0. So that's meaningless to actually calculate it. And then compare the difference with the LSD. So this is the LSD. Remember over here, because we have two level of significance level to calculate, so we need to put in two category over here. So compare your control, the differences with control with the LSD. So to determine, put the signal whether if larger or smaller than your LSD. So 811 compared to LSD of 0.05, which is 453, so it's larger. Compared to 1% significant, 616, it is still larger than the LSD. So 1362 compared to 453 is larger. 1362 larger than 616. 1236 larger than 453. 1236 larger than 616. So do for the rest, and for RS5, 480 definitely is larger than LSD 0.05, but 480 is smaller compared to the LSD of 1% significance. So therefore it has a smaller sign. Whereas RS6, 365 are smaller compared to any of the LSD value of significant level 5 and 1. So smaller. So what is the conclusion? So remember, the conclusion is if the difference is larger than the LSD, then it will be significantly different. Or else it will be not significantly different. So you can make your conclusion. So larger sign or significant. So smaller size, not significant, smaller, not significant, smaller, not significant. So these are your conclusions that you have made. So let's put in our conclusion in words. So the conclusion is RS1, RS2, RS3, and RS4 showed significantly different yield compared to control at alpha 0.05 and 0.01, while RS5 showed only significant difference with control at the significant level 0.05, whereas RS6 did not show any significant differences with the control. So this is your conclusion that you have made. So it's quite easy for LSD. I want you to work on this exercise, and we will discuss this exercise in the class later on. So for this exercise, so you have also done this in your ANOVA lecture. So in short, so this is actually a block design, and you have the block and treatment. This is the result for your ANOVA, and of course the conclude that there are differences between the mean of your block and between the mean of each treatment. So now you need to do a follow-up test to conclude which one are actually different compared to which one. So um, do it before you come to class tomorrow. So when do you use LSD? So you use LSD only when necessary, because you need to compare only like one candidate to another candidate. So if you have more than five groups of treatment, then it is not advisable to use LSD, because it will be too cumbersome. There will be too many steps for you to calculate the differences for each of it. Then I will advise you to do the next approach, to use the next approach. So however, if you are to compare each of the group with only a control, then LSD probably would be fine. So let's look at the second approach for your post-hoc test, which is Duncan's multiple range test, DMRT. DMRT basically do the same. It has the same function compared to the LSD test. It's just that DMRT actually have slightly more steps compared to LSD, but it is good if you have to compare. If there are many treatment groups that you need to compare, then DMRT will be way faster to be calculated based on compared to LSD. So there are 6 steps. The first step, you need to calculate the standard deviation for mean treatment, which is Sx, but the formula is relatively simple. So for both LSD and DMRT, the number that you need to plug from ANOVA table are the same, which is the mean of square for error and the degree of freedom for error. So that's it. So for this one, so you calculate the standard deviation for mean treatment, so which is the square root of mean of square error divided by the number of replicate. Then you calculate the closest significant range, RP. So the formula is this: RP equal to the small rp times the standard deviation for mean that you have calculated. So you have a new table that you need to refer to when you conduct the DMRT, which is the new multiple range test table, which will be provided later on. And after that, arrange all the means that you have calculated for your treatment groups in descending order. Descending order means that from the largest number to the smallest number. And arrange all your RP in sequence next to its means, also in descending order from largest number to the smallest number. And calculate the D, which is difference, the mean minus with the RP that we have calculated. And after that, draw conclusion. It might be a little bit confusing when you do DMRT, but if you do it step by step, it will be actually quite easy to be conducted. I personally prefer DMRT to LSD. So let's look at the same example that we have used before, which is the treatment for grain yield example that we have conducted, that we have calculated based on LSD. So let's use the DMRT to do the post-hoc test for this analysis. So it's the same, but I do not want to repeat for 1%. So for this one, we focus just on the p-value of 0.05. Okay. So for this one, the question will be slightly different. We are not just to compare with the control, but we are going to look at, like, all the treatment groups comparing to each other. That's what the DMRT do. So it doesn't just compare to the control. So you can do all this together. So let's look at it. Okay, so the first step, let's calculate Sx. So Sx, the formula is the square root of mean of square error divided by replicate. So it's pretty simple. This is the ANOVA table that you have calculated during your ANOVA test. So what you need to do is plug in the mean of square error, then divided by 4 replicate. So there are 4 replicates for each treatment group, and you get your Sx, which is 153.93. Then let's move into the second step, which is to calculate the Rp. Okay, so this is the formula for Rp. So where do you get this Rp from? So you get this Rp from the table that we provided over here. Okay, so this is the RP table that you need to refer to later on. So what do we need to, how do we need to calculate the RP over here, the new multiple range test? Is you need two numbers. You need your degree of freedom of error, so which is 21, okay, over here. And you need the second number, which is P. So P over here is actually a range. That's why it's called range test. So this range is from the lowest to the total number of treatment. So there are RS1 until RS6 plus a control. So you have 7 treatment group. So therefore, it need to be, the range will be from 2 to 7. So for the range that you can refer to for your new multiple range test, there's no range number 1. So you always started with 2. The lowest number is always 2. So the range will always be 2 to the max, the number of treatment group that is given in the exercise or in the case study. So for this one is 2 to 7 and at p-value of 0.05. So how do we refer to the table? It will be degree of freedom of error over here, which is 21 is between over here. So 21 is here. And refer to the p number, p range, the number of means for range being tested from 2, so the lowest is 2, to 7 for here. So 2 to 7. So the first one is 0.5. The second one is 0.01. So we are referring to 0.05. So since 21 is in the middle, so we need to get 2.95 plus 2.93 divided by 2. So you get, this one is in the middle, so 2.94, then 3.09, 3.18175, right? So 3.245. So these are the number that you need to plug and fill in for your RP over here. Okay, so 2.94, 3.09, 3.18, 3.25, 3.30, and 3.33. All of these are plugged from the new multiple range test table. And then you need to calculate your RP. So how do you calculate RP? Using this formula, of course. So for P equal to 2, so your RP is actually 2.94 times your SX 153.93, so you get 453, and do the same for the rest. So these are the number that you have obtained, so we will come back to it later on to fill in the table. So let's move into step 3, which is to arrange your means in descending order. So these are the the information given. So you need to calculate the means for each treatment group over here. Okay. So once you have calculated, now you need to rearrange your table, your treatment group from the largest to the smallest in descending order. So RS2 has the largest number, so it will go first, 2,678, followed by RS3, 2,552, followed by RS4, 2,128, RS1, 2,127, RS5, 1,796, RS6 1681, and control 1316, from the largest to the smallest in descending order. And now we go to the next step. Once you have filled in everything from in the descending order, you need to fill in your RP. So the RP is this number that you have calculated over here. So remember, when you fill in, it need to be in descending order also, from largest to lowest. So it means that 513 need to fill in over here, 513. And after that followed by 508, 500, 490, 476, 453. So in this order. So that's how you fill in your RP, which is also in descending order. Descending order for your mean first, only after that fill in RP, which is in descending order. Okay, so then we move into step 5 to calculate the difference. So the difference is mean minus of RP, 513. So 2678 minus of 513, so you get 2165. 2552 minus of 508, you get 2044. 2128 minus of 500, you get 1628. And do the same for the rest. So you do not need to calculate for the smallest one. Okay, so now it comes the tricky part where you need to draw your conclusion. So I will advise you to actually follow my step, do it slowly and in a very systematic way so that you don't confuse yourself. I usually would like to actually label each of these difference A, B, C, D, E, F. If you have like more than G, H, E, like that, you go on, right? So you just label with an alphabet or with any number that you like. And after that, let's work on this one. So let's compare. Look at the mean over here and compare with the difference. Is the mean over here larger than the difference? 2,678 is larger than 2,165. So it's larger than your A over here. So I will label it A. Now move to second one. 2552, compare it to A also. So is it larger? 2552, so it's still larger compared to 2165. So I will label as A. Let's look at the third one. 2128, is it larger than 2165? No, it's smaller. So forget about it. You do not need to continue because it's in descending order. So if this is smaller, of course this will be smaller than A. So you do not need to go on. So let's go back to this one, the RS3 2552, because we are going to compare with B. So is 2552 larger than 2044? The answer is, of course, yes. Then you label B. Just put an alphabet B next to it. And go down. 2128 larger than B? Yes, would be. Then 2127 larger than B? Yes. 1796 larger than B? No. Then you may stop here. Okay? So let's move to C. 2128 compared to 1628. Yes, larger than C. 2127, is it larger than C? Yes. 1796, is it larger than C? Yes. 1681, is it larger than C? Yes. And 1316, is it larger than C? No. Then you can stop there. And let's move to D. 2127, larger than D. 1637, yes. 1796 compared to D, yes, larger. 1681, is it larger than the D? 1637, yes, slightly larger. Then you label with D. And control, compared to D, it's smaller. Then let's move to E. 1796 compared to E, yes, it's larger. Label with E. 1680 larger than E, yes. 1316 larger than E, nope. Then go to 1681, compare with F. 1228, yes, is larger. And 1316 for your control, is it larger than F? Yes, finally, it's larger than F. And you have complete all the numbering over here. So now how do we do our conclusion? So as you can see over here, those with similar number, similar alphabet, they are not significantly different. They are the same. But those that do not harbor the same alphabet, it means that they are significantly different. So that's how you look at it. It means that RS3, RS2, RS3, the same. RS3, 4, 1, they are the same. So it means that anything doesn't have B or C, but these one, they are the same. So it means that RS2 is significantly different compared to control because your control doesn't harbor any alphabet A and your RS2 doesn't harbor any alphabet F. So therefore they are significantly different. So but RS4, 1, 5, 6, they are all the same. RS1, 5, 6, they are the same. RS5, 6, they are the same. So how I would actually do the labeling over here is that because there are so many alphabet over here, is slightly confusing. So we will do in such a way like A and A over here. So we will label small a, RS2, RS3, A. So why RS3 start to have B over here? Because it's B. And then RS4, it's B and C. RS1 is B and C. Why is it D is not there? So we will explain later on. Let's look at RS5 is C. There's no D and E also. R6 is C and D. Control is D. So I renumber over here is because let's look at this one. So when A, so there's something extra over here and B. So two extra here. So I will still keep the B. C, there are one extra, two extra, so I will keep C. But D and E, there's no extra over here. So it means that they are the same. So what does it mean? It means that like all of this harboring C, so RS4, 1, 5, 6, they are the same. When you look at D, RS1, 5, 6 are the same. So it's duplicating. It's actually redundant. It's repeating what C has already concluded. E, RS5 and 6 are the same, but we already know that RS5 and 6 are the same by looking at just C. So it means that D and E, you do not need to actually look at it. it's useless. So it's not informative enough. But F, yes, there's an extra over here because C doesn't give this number. So instead of having D and E over here, so we just remove it so that it's less alphabet and less confusing, and F become D. Um, when we label all of these, we like to use the small alphabet to put next to each of the treatment group. So the one having the same alphabet, they are not significantly different. They are the same. So those that do not have the same, so they are significantly different. So that's how we actually do DMRT. So slightly tricky and confusing over here, but if you get the trick, you actually can do it quite easily. So what is the conclusion? So these are the conclusion. So for RS2 treatment, assume all means are larger than 2165, as same with the B treatment. Thus, the mean treatment RS2 and RS3, they are the same. A and A, RS2 and RS3, they are the same. And BBB, RS3, 4, and 1 are the same. So RS4, 1, and 5 and 6 are the same, and R6 and control are the same. So that's how you can make your conclusion. So in your exam, remember to write each of the conclusion in such a way so that you can get full mark from here. Okay, so that is all for the post-hoc test. So it's actually quite simple. We will work on some example during the class tomorrow. Please get yourself ready. Work on both the DMRT and LSD so that we can do some tutorial in the class. Thank you.